You have a sales file with 1.2 million rows. Each row has a quantity and a price. You need total revenue. You wrote a for loop. It is too slow. In this tutorial, you will learn NumPy Vectorization, how to replace slow Python loops with fast array operations. By the end, you will time a loop against NumPy on the same data and see exactly how much faster it gets. The job is simple. Total revenue equals quantity times price summed across every row. A Python for loop processes one row at a time. It is simple but slow on large data. NumPy processes the entire array in one operation. The loop runs in compiled C behind the scenes. That is what vectorization means. You describe the operation. NumPy runs it on every element without a Python loop. Let us start with the official definition, OpenNumPy.org. They say NumPy is the fundamental package for scientific computing in Python. At the core is the ND array, a grid of values, all the same type, indexed by integers. The key feature, many operations run in compiled code, not in the Python interpreter. Their documentation shows the problem. 2 Python lists, a loop, append the products. That loop works. But on 1.2 million rows, it is painfully slow. Their solution C equals a times B one line. Same math. Runs in C. For us, that means line revenue equals QT times unit price. Whole file at once. NumPy gives you two powers. Vectorization, no explicit loop. Broadcasting shapes stretch automatically. Vectorization means the loop still exists, but in optimized C code, not in Python. That means fewer lines, fewer bugs, and code that reads like math. Broadcasting means operations work element by element, even when array shapes differ, as long as they are compatible. Now let us write the code. Open the project in VS Code. Look at the sidebar. You can see the notebooks folder with sales revenue.ipin. Open it. This first line loads NumPy. Import NumPy as MP gives you all the array tools. Next line, import time. This gives us the perf counter function to measure speed. Last line of cell 1, print the NumPy version. If it prints a number, NumPy is installed correctly. Now cell 2, we load the data. This line sets n to 1.2 million. That is our row count. This line creates a random number generator with a fixed seed. Same data every run. This line generates random quantities between 1 and 5, converts to a Python list. This line generates random prices between 8 and 120, converts to a Python list. Now this line converts the list into a NumPy array. Float 60, 4 means each number takes 8 bytes. Same for unit price. Now both columns are NumPy arrays instead of Python lists. This last line prints the shape. You should see 1.2 million on both arrays. Why does it matter whether we use a list or an array? Here is the difference. A Python list stores pointers. Each number is a separate object in memory scattered around. A NumPy array stores the actual numbers packed together. Same type, same size, side by side. That packing lets the CPU read data faster. Cache works best when values are neighbors. Now let us time both approaches. Same math, same answer. Different speed. This line starts the clock. Time. Perf counter gives the current time with high precision. Next total equals 0. We initialize the running sum. This is the for loop. For I in range n visits every row index. Inside the loop, total plus equals qti list I times price list I, one row at a time. This line stops the clock. Loop s is how many seconds the loop took. This line prints the time and the total revenue. On most laptops, this takes a few tenths of a second. Now the NumPy version. This line starts a fresh clock. This is the key line. Line revenue equals qti times unit price. One operation. Entire array. no loop. This line sums all values. NP_sum runs the addition in compiled C. This line stops the clock. Mil_s is the NumPy time. This line prints the NumPy time and total. Same revenue number, much less time. Both give the same answer. But NumPy finishes in about 1 millisecond instead of 200. You did not write a loop. You told NumPy what to compute, and it handled every row internally. If the totals differ, check that both use the same data and the same D type. Let me highlight the three key lines again. The array line NP array converts raw data into a format NumPy can process fast. The multiply line Qti times unit price applies to every element, no loop needed. The sum line NP_sum adds up 1.2 million numbers in compiled code. For timing, always use time. Perf counter, not time. Time. It is more precise. Why is the loop so slow? Because Python interprets each operation one at a time. For every row, look up the list index, fetch the value, multiply box, the result, add box again. 1.2 million of those individual operations. NumPy does it in one instruction batch. The C code walks through packed memory with a single instruction applied to many values at once. Open a terminal in the project. We will run the same race as a standalone script. Type python revenue race.py. Compare the two times. The ratio tells you the speed up. Now let us talk about universal functions. NumPy calls them ufuncs. A ufunc is a function that operates element by element on arrays. No loop from your side. Examples: NP multiply, NP subtract, NP squirt, NP maximum. They all work on whole arrays. You can write NP multiply of Qti and unit price or just Qi times unit price. Same result. Comparisons work the same way. Is ship greater than 0 returns a boolean array, not a single true or false. Now broadcasting. When array shapes do not match exactly, NumPy can still make it work. Example: line revenue minus a single discount value. NumPy stretches that scalar across every row. Another column minus a row of targets. NumPy stretches both to fill a two-dimensional result. If shapes cannot be stretched to match, NumPy raises an error. That error protects you from bugs. We will cover broadcasting in detail in a separate tutorial. For now, know it exists. Now boolean masking. This replaces if statements inside loops. This line creates a small is shipped array. Some rows are 1, some 0. This line creates sample revenues. 5 rows with known values. This line builds the mask. Is shipped equals 1 gives true where shipped, false where not. This line filters line revenue of mask, keeps only rows where the mask is true. This line prints the result. Only the shipped rows remain. No if statement needed. Len_p where works like an if-else on arrays. True keeps one value, false uses another. NP maximum, NP minimum replace if statements that cap or floor values. Another pattern, computing changes between consecutive values. This line creates hourly sales totals, 4 values. This line computes the change current minus previous divided by previous, all at once using slicing. This prints the result, 3% changes computed without any loop. Category standardization. Subtract the mean, divide by standard deviation. X is equals 0 means compute along columns. Each column gets its own mean and std. Here is forecast error actual versus predicted sales. This one line computes root mean squared error. Subtract square, average, square root. Print the result, one number. No accumulator loop. Now the same timing test in a script file. Open revenue race.py in VS Code. Look at the sidebar. The file is under scripts. It contains both approaches in one file. Line 1 import NumPy as NP. Line 2 import time. Line 3, n equals 1.2 million. Line 4, random generator with seed 7. Line 5, generate quantities as a NumPy array directly. Line 6, generate unit prices. Line 7, convert qti to a Python list for the loop test. Line 8, convert prices to a list too. Line 9, start the clock for the loop. Line 10, sum of qti times price for every index using a generator expression. Line 11, stop the loop clock. Line 12, start a fresh clock for NumPy. Line 13, np sum of qti times unit price, the fast way. Line 14, stop the NumPy clock. Line 15, print the ratio, loop time divided by NumPy time. That is your speedup. If the speedup is close to 1, your data is too small or you accidentally used a loop inside. Now common mistakes. These look right but are actually slow. NumPy Vectorized does not actually vectorize. It still calls your Python function on each element. Converting an array to a list then looping defeats the purpose. You already had the fast format. Iterating with for row in dataframe.iterRows is still Python. Use column operations instead. Appending inside a loop to build a list is slow. Preallocate the array or stay in NumPy. If dtype is object, NumPy cannot optimize. Make sure your arrays are numeric types. Pandas hides this. If you use iteros on a large data frame, you left the fast path. When is a loop actually fine? Small data, one-time scripts, or APIs that only accept one item at a time. For those cases, consider Numba or Python later, but try NumPy first on any large numeric task. Ask yourself, is this math on a large array? If yes, use NumPy. If not, a loop might be fine. Here is the memory layout difference one more time. A Python list, each element is a pointer to a separate object, scattered in memory. A NumPy array, all values packed together. CPU reads them in sequence, fast. Shape tells you the dimensions. Dtype tells you the number type. Ndim is the number of axes. Item size is bytes per element. In bytes is the total array size in memory. One more thing, views versus copies. A slice of an array is usually a view, not a copy. If you modify a view, you modify the original array. Be aware of this. Let us put the final numbers side by side. Loop about 0.18 seconds. NumPy about 1 millisecond. Same answer, 150 times faster. That is the point of vectorization. Remember that traps vectorize is not real vectorization. Iteros is slow. Append in a loop is slow. If you must loop, try compile tools like Numba, but always try NumPy array operations first. To summarize, load your data into NumPy arrays. Describe the math. Let NumPy handle the loop. If your notebook is still spinning on a for loop, replace it with array operations.